we can classify chemical reactions with respect to their reaction order, and they can be zero order, first order, second, third, mixed order, higher order. A zero order reaction is a reaction that has a constant reaction rate. The reaction rate is independent of the concentration of the reagent. In a first order reaction, the reaction rate is proportional to the concentration of the reagent. So the reaction rate will double when the amount of reagent is double. In a second order reaction, the reaction rate will quadruple when the reaction is double. In a third order reaction, the reaction rate will increase 8 times, when the reagent is double. This is an example of a zero order reaction in which the reaction rate is constant, is independent of the concentration of the reagent. So here's, we've got in the y-axis the concentration of ethanol in blood, and in the y-axis, in the x-axis, times in hour. And as you notice, between 1 and 4 hours, these 2 points here, the concentration of ethanol in blood decreases steadily and is not dependent on the concentration of alcohol. It decreases at a constant rate. That is an example of how a zero order reaction looks like. In a first order reaction, the rate of reaction is proportional to the concentration of the reagent. When the rate of reaction, it will double when the amount of reagent, the concentration of reagent is double. So if we express the rate of reaction as K times concentration of the reagent A to the power of X, for a first order reaction, X equals 1. K is what we call the rate constant and is particular to particular reactions. So if we differentiate the rate differential of concentration A with respect to T, we come up with the differential rate law, in which the rate is directly proportional to the concentration of the chemical. And you can write this as in this exponential form, or you can write it as an integrated rate law using natural logarithms, and you come up with this expression. How would you work out if a reaction is zero order or first order? Well, if it's zero order, it's reasonably straightforward. If you plot the concentration of the chemical versus time, and it gives you a straight line, that's a zero order reaction. When it gives you a curve, that means that that reaction is not zero order. The concentration of the reagent does play a role in the speed of the reaction, and then you can look at whether that reaction is going to be first order. And to know if a reaction is a first order reaction, you need to plot the natural logarithm of the concentration versus time. And if this yields a straight line, then you know that particular reaction is a first order. And the slope of that straight line will be the negative value of the rate constant. So you can use graphing information on concentration of chemicals versus time to determine the reaction, the order of a particular reaction. This is an example of a first order reaction, the radioactive decay of iodine 131. And as you notice, if you represent milligrams of iodine in iodine 131 versus time, it gives you a sort of exponential decay. So that's clearly not a zero order reaction. If instead you represent the logarithm, the natural logarithm of that milligrams of iodine 131 versus time, that gives you a straight line, and the slope of that straight line is minus k, the negative value of the reaction rate constant. A reaction rate can be also second order, and when a reaction rate is second order, then x equals 2. And you can have that in two ways. You can have, for example, a reaction in which the reaction depends on one reagent, and that will give you K times square concentration of A to the power of 2. But you could also have a second order reaction depending on two different reagents. and that will give you a reaction rate of K times concentration of A times the concentration of B. And again, you know, those two powers, 1 plus 1, 2, that would still be a second order reaction. So you can have it in a differential way, or you can have it in an integrated way. And if you have it in an integrated, you know, if you integrate that expression, you end up with this expression. So how do you know if a reaction is a second order process? Well, if you represent 1 upon the concentration of A versus T time, and it yields a straight line, that means that process is a second order process. And the slope of that process is the rate constant. So as a summary, a zero order process will give you a straight line when you represent the concentration versus time. A first order reaction will give you a straight line if you represent the natural logarithm of the concentration versus time, and a second order process will give you a straight line if you represent the 1 upon the concentration versus time, and it gives you a straight line. This is an example of a second order reaction, the decomposition of nitrogen dioxide. 2 moles of nitrogen dioxide produce 2 moles of nitrogen monoxide and 1 mole of molecular oxygen of O2. If you represent the natural logarithm of the concentration of nitrogen dioxide versus time, you see that's not a straight line, so that cannot be a first order reaction. When we represent 1 upon the concentration of nitrogen dioxide versus time, that gives you a straight line, and that the slope of that line is the rate constant for the reaction. So I'm going to ask you to solve an exercise and work out what is the reaction order for this particular reaction and what's the rate constant for the reaction. And this is the hydrolysis of cisplatin, which is an anti-cancer drug, one of the first ones ever produced, which needs to be hydrolyzed first before it is active. So the active form removes one of the chlorides of the structure and introduces a molecule of water. And you've got 2 sets of information that you can use to work out whether this reaction is zero, first or second order. One is a plot of concentration of cisplatin, well, cisplatin or chloride anions, depending on which line you look at, with respect to time. And the other one is a set of experiments in which the concentration of cisplatin was changed and differing initial rates were measured. So you can do this in 2 ways. You can either look at the data points from the graph, for example, looking at cisplatin, how the concentration of cisplatin varies in time, and then work out if it's a zero, first or second order reaction by representing the appropriate y-axis with respect to time. Or you can look at the initial reaction rates when the concentration was changed and see if you can work out whether the rate is affected or is proportional or is double, etc., to work out the reaction order. So stop the video now, please. So I hope you have stopped the video and had a go at the exercise. The first thing I can see straight away is that the reaction is not zero order, because well, we can see clearly both in the graph the concentration of cisplatin changes with time, or here when we have different experiments and different reaction rates, that the initial concentration of cisplatin is affecting the reaction rate. So it cannot be zero order because it is dependent on the cisplatin in some shape or form. The next step would be to work out is a first order reaction, and for that you need you can do it in 2 ways. One would be taking all these data points, or at least some of them, and represent the natural logarithm of those values versus time and see if you get a straight line. Another way, which implies fewer calculations in this case, is because you have initial reaction rates for a series of experiments, see if you can spot a pattern in how those reaction rates change when the concentration of cisplatin, the initial concentration of cisplatin, changes. And I can see that when the concentration of cisplatin is double, the reaction rate, the initial reaction rate, also doubles. That tells me that the rate of this reaction is directly proportional to the concentration of cisplatin. And that is the definition of first order reaction. The rate is proportional to the concentration of cisplatin, and whatever makes the proportion is this times that concentration, that rate constant. So how would I go about, we have already established the first order reaction, and now the question also asks me to identify or to calculate the rate constant. Well, for that, I will just pick one of the points in the experiment. In this case, I've chosen experiment 3. I would pick up that rate divided by the concentration of initial concentration of cisplatin for that particular experiment, and that would give me K for this reaction. Half-life, or T1.5. Half-life is defined as the time required for 1/2 of a reagent to react. So the concentration of the reagent at T1.5 will be half the original concentration. With this information, and using the different rate laws, we can work out how we can calculate T1.5 half-life for the different reaction orders. So we take the reaction for the first order reaction, the integrated rate equation, and we substitute the concentration of A at times T by 0.5 initial concentration, which is the definition of half-life, sorry, and that gives us, well, this. If you notice, in a first order reaction, half-life does not depend on the initial concentration. It's just related to the type of reaction you have, because K will be different, but it does not depending on how much reagent you start with. In a second order reaction, again, we take the integrated rate law, and we substitute the concentration at times T.5 by 0.5 initial concentration of the reagent. We simplify the equation, and we come up with this expression for the half-life in a second order reaction. And as you can see here, the initial concentration of the reagent does play a role in when that T1.5, when that half-life is achieved. This table is just a summary of reaction orders and half-lives for a 0, first, and second order reaction. And you have slightly two versions of second order reactions. One would be when the reaction is second order, but with respect to one particular reagent. So you have two molecules of that reagent reacting, and that's the examples we have looked previously. But you can also have a second order reaction by having the reaction rate depend on the two reagents, because those two coefficients will add up to 2, so it's still a second order reaction.